Hello, just going to get started on the energy topic. So this is option C, and I'm looking at doing part B1 today. So let's get started. So as always, I'm going to start with the study guide, and I'm looking at basically covering all of these today. One that will carry over throughout the entire topic, though, is the advantages and disadvantages of the different energy sources. A lot of them are sort of general knowledge, but we are going to specifically talk about advantages and disadvantages as we study the different types of energy. Okay, so let's get into it. So the energy sources we're going to be talking about are fossil fuels, nuclear fusion and fission, and solar. For the HL, we talk more about nuclear and solar, and we also talk a bit about electrochemical cells. So before we get into this section, we might want to do a quick recap of redox. Okay, so let's go on. So renewable versus non-renewable. So renewable, non-renewable. So a non-renewable source is one that can't be generated. So examples here, things like fossil fuels, Fuels. Be good if I could spell. We've also got nuclear fission. Nuclear fission. And on the other side, we've got renewables. So renewables can be things like biofuels. So for example, fuels like ethanol, for example. So ethanol can be used as an additive for petrol, and it's derived from corn that's grown. So renewable sources are ones that we can make or that regenerate themselves without us trying. So biofuels, solar. We've also got things like hydro and tidal. So renewable sources are generally seen to be the quote unquote better, but in a lot of ways there are some really solid reasons why non-renewable sources such as fossil and nuclear fuels, why we still use those for a lot of the base load of our energy demands in society. So we are going to talk more about that as we get into those types of fuel. All right, so when we talk about quality and quantity of energy, so the quality of energy, and my brain just went into a Shakespeare monologue. The quality of energy is talking about, is it useful? Is that energy in a form where I can extract in most cases for us, electrical energy from it? Is that energy in a form where I can harness it? When we talk about quantities of energy, we can talk about them in terms of kilojoules or joules. We can also talk about them in calories if we're talking about food. And quantities we generally express using some formulae on the next slide as kilojoules per gram or kilojoules per cm3. So how much energy do I have for the amount of fuel that I need to transport? So something that's super high in energy but takes up a lot of room isn't as useful for something that maybe has slightly less energy but is much more transportable. Okay, let's continue on. So there are two different formulae for how we can calculate the quality of energy. Sorry, the quantity of energy. So we have energy per volume. So this is going to be in CM3 or DM3. And that's super useful for liquids and gases. The massive fuel consumed, that's far more useful for solids, and that's done in either grams or kilograms or tons or megatons. So that massive fuel is a much more useful measure for a solid substance. So what is the specific energy of candle wax? What is the specific energy of uranium fuel? As opposed to what is the energy density of octane, which is one of the main components of petrol. What is the energy density of hydrogen gas? Let's keep going. Okay, so let's do these calculations just as some practice. So this formula I got directly from the study guide. These two lines are directly from the data book. So let's work out the specific energy for octane. So what this is saying is for 1 mole, sorry, I'll write over here and I'll change colours because that's a bit light. So for 1 mole of octane, which is C8H18, it releases, because it's an exothermic reaction, it releases, and now I can't read the bloody number, it releases 5470 kilojoules of energy. So we need to work out 1 mole of octane is how much mass of octane. So MC8H18 is equal to moles times molar mass, and I'm saying for 1 mole. So I've got, oh, that's still a pen. I have 1 mole, so 1 mole, and then we have times 8 times 12.01 plus 18 times 1.01. So let me just grab a calculator and do that, and I'll be back in a moment. So that is 114.26 grams. So specific energy is energy divided by mass. So 5470 div 114.26, which equals 5470 div. My answer gives me 47.9. 47.9 kilojoules per gram. One thing that's super important with these is you've got to make sure that you are giving units, because we're not specifying the units that the energy is in or the units that the mass is in. You've got to make sure at the end you specify what units you are giving that specific energy in. So when you are doing this, you have to make sure, as I've said, you give a number and you give a unit. Okay, so that's specific energy. let's move on and look at the other formula. So, the energy released from my fuel divided by the volume of fuel I consumed. So, we worked out before that for 1 mole of octane, C8H18, it was 5470 kilojoules of energy. And that was 114.26 grams. C8H18 gave me 5470 kilojoules. Now, I need to convert that into a place where I can use my density. I need to convert between the mass I've got into a volume. So, let's go. So, density is mass on volume. Let me move this over a bit. So, density is equal to mass on volume. We are told that it is 703 kilograms, so I need to convert this to 0.11426 divided by volume. So you multiply both sides by V and then divide 0.114 by 703. So divide by 1. Sorry, I'm speaking my calculator right now. So it's 0.11426 div 703 gives 1.625 by 10 to the neg 1234 M3. So I've got a volume. Let me go back to my laser pointer. I've now got a volume and I've got an energy. So let's do back to pen, and I might switch colours to differentiate the calculation. So I've now got energy density is energy divided by volume. So this is 5470 div 1.625 by 10 to the neg 4. So in my calculator, I'm just going to type 5470 divided by my previous answer gives me a very, very large number. So my calculation is saying that it is 3.37 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7 kilojoules per M3. I'm going to pause this here and see whether I can get a literature value to back me up on that. So yes, it actually turns out that that number was correct, because this is 33433 megajoules per M3. And when you do the unit conversion from the number I came up with last slide in kilojoules per M3, there's some rounding differences. I'm using a different source by using the data book, but those two things are roughly equal. It seemed like a huge number. That's why I wanted to double check. Okay, so when it comes to choosing fuels, there are a couple of things we need to keep in mind. We need to look at that energy density. We need to look at how easy something is to transport. So something like hydrogen gives off an awesome amount of energy, but it's like Hindenburg, it's an explosive substance. So we need to keep that in mind when we're looking at transport and use. Something like uranium has incredibly high specific energy. But you want to be able to drive a car without wearing lead-lined knickers, so it's not really appropriate for that. So energy density, ability to transport, and then really our sort of tertiary concern are environmental byproducts and issues around surrounding the environmental. Okay, so these are really what we think about. So I know I've just written energy density. It's also that specific energy when we look. So when we're choosing fuels, these are our sort of top three concerns. So the law of conservation of energy. It's something that we will mess with slightly when we start talking about nuclear, but for our purposes right now, the law of conservation states that we can't create or destroy energy. So, if I have in the fuel tank of my car, if I have, let's call it 1000 kilojoules of the chemical energy of my petrol. What percentage of that do you think ends up being used to actually drive my car, the kinetic energy of my car? So let's think about, instead of just showing one arrow, so petrol to tyres to wheels spinning, let's break it down. So my petrol goes into my engine. From there, it's exploded and it's turned into kinetic. There's then another process where it's moving pistons, which is more kinetic, and then it goes through a whole bunch of these steps. Every time we do an energy conversion, we are always going to quote unquote lose energy. And this is losing energy to the environment, not losing energy out of the entire universe, because that can't happen. Law of conservation of mass. But this lost quote unquote energy is usually, in the cases of something like a car and in a lot of other energy transfers, it's being lost quote unquote as heat. So if this were a perfect energy transfer from my petrol to the kinetic energy of my wheels, the bonnet of the car would not warm up. The tyres where they met the road would not warm up. It's all of this quote unquote lost energy as we go. That's what causes my engine to heat up. That's what causes the axle of my car to heat up. That's what causes my wheels to heat up. All of these energy transfers lose some energy. So that's when we talk about transfer efficiency. So the useful outputted energy. So if you're looking at a light globe, the useful outputted energy would be light energy. If you're measuring the energy efficiency of a car, it would be kinetic versus chemical. So we've got your output energy, and this is useful. So for example, if you're looking at a stereo or a TV, the TV is a better example, the useful energy would be light and sound versus the inputted energy. So it's basically output divided by input times 100. It gives us, as you can tell, a percentage. So what percentage of the energy did I put in actually came out in a useful form, in the form that I wanted it to be in? Okay, let's continue on. So let's quickly have a recap of what we talked about. We talked about what is useful energy. We talked about quality of energy as degraded as heat gets transferred to the surroundings. One thing that I will talk more about later on is energy and materials going from a concentrated to a dispersed form, because that actually ties in super nicely to something we'll talk about in HL called entropy. I'll talk more about that in a separate presentation. We've then got, I need my yellow back. We've talked about renewable versus non-renewable. We've talked about energy density, specific energy, and efficiency. We've talked about calculating the energy density and specific energy from the enthalpy of combustion, the density, and the molar mass. We've done that one. We've talked about how we choose fuels, and we've talked about, we discussed the efficiency, but we didn't actually determine it. I might leave that till next presentation. So next presentation, I might bring in a little bit of talk about entropy. I might talk about how we use different types of renewable and non-renewables. And I might actually do a calculation for efficiency. This last point we will be doing over the course of the unit. For every single one of our types of energy, we are going to discuss advantages and disadvantages. Okay, thank you so much. Have a fantastic rest of your day, and I will see you next time.